All right, section 2 is probability. So this is the section that we've been really trying to prepare for with throwing dice and playing cards and throwing darts and talking about all those ways that those things can occur. So this really comes into play here. There are two types of probabilities that we have been discussing. So there's two types of probabilities that we will discuss in this section. Theoretical probability and experimental probability. Experimental probability is things that you take data on, and then from that data you make predictions based on what you have seen. Theoretical probability is when you go through and analyze what it is that you're looking at. Like, for example, the dice. We analyzed how many different ways we could throw two dice. That was theoretical probability. And then we collected data on that, and we found that our experimental probability from the data was very similar to the theoretical probability from the dice. So, experimental probability is a probability that is calculated through data collected through observations or experiments. You're not using mathematical theory. Theoretical probability is calculated from a sample space of equally likely outcomes. That's where we analyzed every possible way to roll two dice mathematically. We actually rolled two dice here experimentally. Now this phrase sample space, that's a new one. The sample space is just the set of all possible outcomes. And what I told you guys before is that probability is best calculated using wins over ways. Keep that thing in mind. Just like with the fundamental counting principle, you're drawing out dashes. With probability, if you're always remembering wins over ways, that will always help you set up your probability problems. The sample space is the ways. So I could technically say wins over the sample space. The sample space is just all of the possible ways that something can occur. Or, that's theoretical probability. An experimental probability would be all the ways that things have occurred in our experiments that we've tried. All right, as usual, there's some notation that we need to learn. The notation for probability is P, and then in parentheses, some sort of event. It's kind of like function notation. Inside here, you write whatever the event is. You won't write the word event. So like the probability of rolling 12, a sum of 12 on two dice. You'd write 12 here. For experimental probability, the formula is the probability of whatever that event is equals the number of times that the event occurred divided by the number of trials that you had. So you could come up with an experimental probability from your data for how many times you dealt a pair when you were dealing two cards out, and then divide by 50 because that was the number of trials that you had. Okay? This is still wins over ways. It's just a little bit different than usual. It's how many times did we see what we're looking for divided by how many trials did we do, how many pieces of data do we have. So for example, this is an experimental probability here. Of the last 60 vehicles going by on the highway, 15 of them were motorhomes. Because it's getting to be that season again. What is the experimental probability that the next vehicle will be a motorhome based on the information that we've been given here? This is an experiment that we're performing. There's no number theory behind it at all. We're just basically sitting here and counting stuff. And then there you go, the next vehicle was a semi. Close, yeah. It was definitely not a car. All right, so what do? Well, we do wins over ways. The number of times that the event occurred is my wins. So I'm going to write P. What am I looking for? So probability of a motorhome equals wins over ways. How many wins did I have for this? There were 15 motorhomes that went by out of how many things went by? 60. So then that's your probability, your experimental probability. that fraction reduces down to what? 1/4. So 1 out of every 4 vehicles that goes by is a motorhome. And if I want to write that as a percent, what percent would that be? 25. Yep, that's 25%. That's 1/4. 1/4. 15/60 reduces to 1/4. So you could be asked to write your answer a number of different ways. You could be asked to write as a fraction. You could be asked to write as a decimal or as a percent. So just make sure you're paying attention to how the answers are asked to be given, or look in the back of the book and see if they're writing their answers as a fraction or a percent. That'll be your clues on the homework. All right, go ahead and do the second one. A softball player got a hit in 20 of her last 50 at-bats. What is the experimental probability that she'll get a hit in her next at-bat? Give me the fraction probability and also the percent. Yeah, it would be. All right, what do we do? No, probability of a hit. We're looking for a hit in her next at-bat, so it's probability of a hit equals the number of hits that she's gotten since we started keeping track, divided by the number of at-bats that she had, which was 50. And like you said, what are we calculating here actually? Basically, this is your batting average. Yeah, it's a prediction of how often you get a hit every time you come up to bat. So 20/50 reduces down to 2/5. So basically, she's getting a hit 2 out of every 5 at-bats, which is pretty good. As a percentage, that would be what? 40%. So 40% of the time, she's getting a hit. As a batting average, she would be batting 400. Well, Babe Ruth was a strikeout king. So, well, batting average of 400, if you were a softball player, you'd be pretty happy with that. Most professional baseball players have a batting average like in the low 300s or in the high 200s. Okay, theoretical probability now. Each outcome must be equally likely to occur. So that goes to when we're rolling dice or drawing a card out of a deck of cards or pulling a marble out of a bucket or something. Each outcome is equally likely to occur. So for example, rolling a die, which we know is a random number cube, drawing a card from a standard deck of cards, pulling a marble out of a bag of marbles, etc. The formula is the probability of that event, whatever it is equal to wins over ways. It's that simple. So what's the probability of getting a 5 on one roll of a die? One die, I roll it. What's the probability of getting the 5? Yeah, so the probability of a 5 is equal to, there's only one way to get that 5, but there's 6 ways to roll a die. So there's one win out of 6 ways, 1/6 is the probability. Yes, it's wins over ways, okay? So that means the numerator is how many wins you have. In other words, if I roll a die, how many different ways are there for a 5 to come up? How many 5s are on a die? There's only one 5 on the die, right? So it has to come up 5, and there's only one way for that to happen. So I get a 1 right here. But then divide by the number of ways that you can actually roll a 6-sided die. How many ways are there to roll a 6-sided die? There's 6. So that's why this is 1/6, wins over ways. How about getting a sum of 5 on one roll of 2 dice? Yeah, we got to remember how many ways we can roll a 5 for a sum. Well, okay, so let's list them out. How many different ways can we roll a 5? 1, 4, 2, 3, 3, 2, 4, 1. So if you're lost, if you don't have your data sheet in front of you, which on a quiz or a test you won't, you can just do that. Just think of the ways to roll a 5, all right? How many ways are there to roll a 5? There's 4. So we have 4 out of how many ways to roll 2 dice? 36. So 4/36, which of course reduces to 1/9. That's a 1, 9th. There you go.
So how would we write the notation?
There are always several ways that you can go about solving a problem. With this one, getting a sum that is odd on one roll of 2 dice, you got to kind of think about this a little bit and maybe even go through some different ways that you can roll an odd sum on dice. So let's think about this. How many ways can I roll an odd sum? What are my odd sums? Can I roll a 1? No, I can't roll a 1. So it's 3, 5, yep. Okay, so those are the only ways that I can roll an odd sum. So now what I need to do is figure out how many of each of those numbers, how many different ways can I roll each one of those sums? So how many different ways can I roll a 3? 2. 2 and a 1 or a 1 and a 2. How many different ways can I roll a 5?
4.
There's 4. We just figured that one out up here. How many ways can I roll a 7?
6.
There's 6 ways to roll a 7. How many ways can I roll a 9?
4.
There's 4 ways to roll a 9. How many ways can I roll an 11? 2. So now I can add all of those numbers together, and that will give me my wins for my numerator. What do we get? 6 plus 6 plus 4 plus 2 is 18. That's my wins. How many ways are there to roll 2 standard 6-sided dice? 36. So 18 over 36, which reduces down to 1/2. Half of the time you will roll a sum that is odd. And if you think about it, shouldn't that make sense? It should make sense. So there you go, half of the time. 8, 9, 13 through 16 all. They're all very similar to this. Basically just keep thinking wins over ways. Work with your partner if you want to, but work on them right now. So this next part takes wins over ways and combines it with what we learned last time with permutations and combinations. And when you do that, you wind up with that word, whatever that is. What is that? Combinatorics. Sorry, yeah. Combinatorics? Combinatorics? I don't know. But that's that word. And this is what they're talking about when they use that word. When you have an equally likely amount of outcomes, it is usually easier to find theoretical probabilities using the fundamental counting principle, which is what we learned in the last section, and permutations and combinations together. So we're taking both of those ideas and putting them together. To use these to determine the wins and then divide by the ways. So you're still doing wins over ways. You're still using the fundamental counting principle, which means event times event. And now you're also using permutations and combinations, which was NCR or NPR. It all gets slapped together here. Excellent. All right, so for example, determine the theoretical probability of, not each, determine the theoretical probability from a standard deck of cards. And this problem right here, the number of combinations of 2 of the 4 7s. I want to add to this in a 5-card hand. So this right here is the example. I want to determine the number of combinations of the 2 of the 7s in a 5-card hand, which means in this hand I will have 2 7s and then 3 other cards. Okay? I just want a pair of 7s. Now, to do this, we need to determine the number of combinations of just getting 2 7s. So that is, do I care what order I get the 2 7s? Do I care what 2 7s they are? As long as I get 2 7s, right? So is this a permutation or a combination? So this is not this problem right here, just down on the side here. I just don't like the way that I worded this. I want any 2 7s. That is a combination. How many things do I have to choose from? How many 7s do I have to choose from? 4. How many am I choosing? 2. So any 2 7s. I have 4 7s. I'm choosing 2 of them. That's 4C2. Next, the number of combinations of 3 cards drawn with the 7s removed. So I'm talking about the 7s here. Now I want these 3 other cards. So the number of combinations of 3 other cards that aren't 7s in a deck of cards. How many cards are in the deck then if there are no 7s in the deck? 48. Does it matter what order I get those cards or what those cards are? No, so this is a combination. And how many cards am I getting here? 3. So the number of combinations of 3 cards drawn from the deck without the 7s in the deck is 48C3. The reason that the 7s aren't in the deck is because I'm talking about them here. There are 4 7s in the deck. If I take out all 4 of those 7s and then I pick 2 of those 4 7s, this is how I get those 2 7s. This is how I get my 3 other cards. The number of 5-card hands that includes a pair of jacks is basically the same thing. Not jacks, by the way. We're going to change that to 7s. So the number of 5-card hands that includes a pair of 7s. To do that, we need wins over ways. How many 5-card hands that I can get? Sorry, this up here is wins over ways. The number of 5-card hands that include a pair of 7s now. Well, this is how I get 2 of those 5 cards. This is how I get my 2 7s. And this is how I get my 3 other cards. So if I'm talking about the fundamental counting principle, event 1 is me getting these 2 7s. Event 2 is me getting those 3 other cards. So the fundamental counting principle says event 1 times event 2. Event 1 is me getting those 2 7s, 4C2. Event 2 is me getting those 3 other cards with the 7s removed, 48C3. So there's 2 events going on here. The event of me getting those 2 7s, and then the event of me getting those other 3 cards. The way that I get 2 7s is there's 4 7s, and I'm choosing 2 of them. The way that I get those 3 other cards is now there's not those 4 7s in the deck anymore because I already took care of that. 48C, give me 3 more cards. That is how I get the number of 5-card hands that include a pair of 7s. How many 5-card hands are there total in the deck? So if I want a 5-card hand, does it matter what order I get those cards? No. So is this a combination or a permutation? It's a combination. So how many cards do I have to choose from? 52. For any old deck of cards, there's 52 cards in the deck. How many cards am I getting? 5 cards. So what I've done here is I've broken this problem apart, and you're probably sitting there going, what in the world is going on? What I've done is I'm trying to determine the probability, the theoretical probability, which means I need wins over ways. Well, the ways is sitting right here. How many ways can I get dealt a 5-card hand? 52C5. There's 52 cards in the deck. I'm choosing 5 of them. This is the number of ways I can get a 5-card hand out of a deck of cards. So then, the number of wins that I have is I have to create that hand. So 4C2 gives me the 7s. 48C3 gives me the other 3 cards. Those are my wins. This right here is my wins. So this is my pair of 7s. This is my other 3 cards. This is my wins right there. So now when I do wins over ways, I have 4C2 times 48C3, and that's divided by my ways, which was 52C5, the sample space. Type all that into my calculator, and it will give me an answer. And that will be the probability of me being dealt a pair of 7s when I'm dealt 5 cards. So you get 0.03992 something or another, but you want to make that a percent. So this would be 3.99-ish% of the time. You'll get a pair and then 3 other cards. What is the probability of being dealt all 4 aces in a 5-card hand? So now we don't want a pair of 7s, we want all 5 aces. So this is going to be split again. We're going to do wins over ways. But in the wins portion, there's 2 events. What's one of them? We need all 4 aces. What's the other event? One other card. Yeah. Now in the bottom, it's going to be the ways. How many ways are there for me to be dealt a 5-card hand? 52 C5, yeah. There's 52 cards in the deck. I'm choosing 5 cards. Okay? So that's the sample space there. That's the ways. Yeah, because there's no specific order. Okay? All right, so let's take out the aces event first. Does it matter what order I get those aces? No, so that's a combination. Now, how many aces are in the deck? 4. How many aces am I getting?
4.
I want all 4 aces. So it's 4C4. Times, now the event of the other 1 card that I got to get. How many other cards are there in the deck? 48 other cards. Does it matter what order I get that 1 card? No. So it's going to be a combination, 48, and I'm getting 1 card. So over here, I'm choosing 4 cards. They are all aces. Right here, I'm choosing 1 card. It can be anything it wants to be. That's the setup for wins over ways. And when you do that, what do you get?
5.
It's not 5. 184. So if you were to make that a percent, it would be 0.0. How many zeros did you have?
4.
Okay, so 4 zeros in the decimal, so that means there's 2 zeros here. 0.00184% of the time, you would get all 4 aces dealt to you in a 5-card hand. That's an incredibly small percentage. Basically, it's never going to happen. Finding geometric probabilities. So this is where the darts come into play. Geometric probabilities are found using area, using the same ideas presented so far. So assuming one area is equally as likely to occur over another, like you're randomly throwing a dart at the dartboard, which makes any area on the dartboard equally likely to come up, then you can use this probability. The area of the wins divided by the area of the ways. So, classic example is a pitcher throwing a ball into a strike zone. This little region right here is where the pitcher is trying to throw because this batter can't hit these pitches. So he's trying to throw the ball in there. It's a little window, 4 inches by 6 inches. The strike zone itself is this whole area here. What is the probability, assuming that the pitch goes into the strike zone, what is the probability that that pitch winds up right there? Well, it's an easy one to figure out. All you got to do is area of the wins. This is the wins right here. What's the area? 24 divided by the area of the ways, which is this whole area right here, 17 times 22, whatever that is.
First one, 374.
So then reduce that down to a decimal, and what do you get? 6.41%. So that has a 6.41% chance of landing in that particular spot in the strike zone. That's how you do area probabilities.